Hi everyone, let's graph some polar curves. We're going to treat these as polar equations. Now, in our class, you're going to be graphing circles with arrows on them. It does get more complicated later on in Math 151. But for right now, in example 1, let's sketch the graph of the polar equation, r equals 2 sine of theta, where r and theta are polar coordinates. Now first, I think it helps a lot to graph these as Cartesian coordinates, where r is like the y coordinate and theta is like the x coordinate. So I think it's helpful to first graph r against theta as Cartesian coordinates. So here, we're graphing one cycle of r equals 2 sine of theta. It's your classic good morning graph, where the amplitude is 2. Now, we're going from 0 to 2 pi, and using the frame method, I'm breaking things up into quadrants. The quadrantal angles break things up into 4 quadrants. And these 4 quadrants will correspond to 4 phases. In the basic examples we do in our class, it's enough to look at these 4 quadrants. In general, for the more complicated examples, which I'll discuss later, then we can get a new phase whenever theta changes quadrant. Of course, that's the case in our examples. And then later on, beyond this, watch out for when r changes direction from increasing to decreasing, or vice versa. If r changes direction, we need a new phase. Also, if r changes sign, we need a new phase. But fortunately, in our basic examples, like over here, r will change direction and r will change sign only as we cross over quadrantal angles. So it's sufficient to just look at things in terms of quadrants, at least for our basic examples here. So now we're going to trace the behavior of r as theta changes through these phases. In phase 1, in phase 1, theta is increasing from 0 to pi over 2. R is increasing from 0 to 2. So here in phase 1, again, as theta increases from 0 to pi over 2, r is increasing from 0 to 2, meaning that if you imagine a particle that's going to trace out this curve, the particle is going to be moving away from the pole. Moving away from the pole or origin. And because r is basically positive in quadrant 1, then that means that, well, according to theta, we think we're moving in quadrant 1, the particle is moving in quadrant 1, and because r is positive here, in fact, the particle is moving through quadrant 1. I'll put this in purple. Quadrant 1 and moving away from the pole. Now, in quadrant 2, as theta goes from pi over 2 to pi, r is decreasing from 2 to 0. R is getting closer to 0. It might be helpful to think of, is r moving closer to 0 or away from 0? Is r moving towards 0 or away from 0? Okay. And then if this behavior changes, we get a new phase. Right? Okay, so here r is going from 2 towards 0. So as theta goes from pi over 2 to pi, in what we think is quadrant 2, r is decreasing from 2 to 0, meaning that we're moving towards the pole in phase 2. Now, as theta increases from pi over 2 to pi, we think we're in quadrant 2, and because r is positive here, yes, in fact, we are in quadrant 2. The particle is moving through quadrant 2. All right. So let's see what we have so far. First, r increases from 0 to 2. We're moving away from the pole in quadrant 1. Then r decreases from 2 to 0 in quadrant 2. We move towards the pole. So let's look at the graph we get. All right. First, using Cartesian graph paper, and then in polar. All right. So again, in phase 1, We think we're in quadrant 1. We are in quadrant 1. R is positive in here, right? And when theta equals 0, R equals 0. When theta equals 0, R equals 0, all right? That means that we start at the pole or origin when theta equals 0. We move away from the pole until when theta is pi over 2, R equals 2. When theta is pi over 2, R equals 2. So we're at this point here, the North Pole. And then as theta moves from pi over 2 to pi, R decreases from 2 to 0. We're moving towards the pole through quadrant 2. And you need to put these arrows on here, at least put one arrow here, indicating orientation. Desmos doesn't do this. You need to put the arrow here indicating orientation somewhere. Basically, we're always going to be going counterclockwise. In polar graph paper, right, again, we start at the pole when theta equals 0, R equals 0. So when theta equals 0, we start at the pole. Again, as theta increases from 0 to pi over 2, R increases from 0 to 2. So we're moving away from the pole. The distance from the pole is increasing. As the angle increases, here's pi over 2 over here, and we're at the North Pole over here. Maybe put the arrow here. You got to put an arrow at some point. And then as theta goes from pi over 2 to pi, R goes from 2 towards 0. We're moving towards the pole. The particle is moving towards the pole. And at theta equals pi, we're at the pole. R equals 0. We're at the pole. We hit the South Pole here. All right. Now, actually, I claimed that we're done. But let's see why that is. Let's verify that. Let's go through phase 3 now. As theta goes from pi to 3 pi over 2, right? R is going from 0 to negative 2. We're moving away from the pole. Okay, R is moving away from 0. We're moving away from the pole. But what quadrant are we in? See, if theta is going from pi to 3 pi over 2, we might think we're in quadrant 3. That would be true if R is positive. But wait, R is negative. So we're not going through quadrant 3. We're going through the opposing quadrant, quadrant 1. So we're actually moving through quadrant 1 because R is negative here in this phase. R is 0 over here at pi. Okay. So what does that mean? Let's think about this. So in phase 3, we're in quadrant 1. We're moving away from the pole. R is going from the pole to 2 units away from the pole, but in the wrong direction. All right. So we're in quadrant 1. We're retracing the steps here. We're in quadrant 1. We're moving away from the pole until we're 2 units away. So instead of going through quadrant 3, all right, the thing is R is negative in phase 3. So we don't go through quadrant 3. We're actually going through quadrant 1. We're actually going through quadrant 1. So instead of going this way, instead of going on this ray, we're on this ray. Instead of this ray, and so forth. We're retracing our steps. In phase 3, we're retracing our steps. We're redoing phase 1. And likewise, phase 4 will redo phase 2. In quadrant 4, all right, theta is going from 3 pi over 2 to 2 pi. R is going from negative 2 to 0. If R is approaching 0, we're moving towards the pole. Okay, now in here, we think we're in quadrant 4, but wait, R is not positive, R is negative. So we're not in quadrant 4. I'll do this in green. We're not in quadrant 4. We're in quadrant 2, the opposing quadrant. Remember, 1 and 3 are opposing quadrants, 2 and 4 are opposing quadrants. If R is negative, you flip to the other one, the other opposing quadrant. So again, in phase 4, we're redoing phase 2. We're in quadrant 2, and we're moving towards the pole. We're in quadrant 2. We start off 2 units away from the pole in the wrong direction. We're supposed to be down here, but we're actually up here because R is negative. R is negative 2. We're at the North Pole. And instead of going like so, we're going like so through these angles. We're going through quadrant 2, not quadrant 4. And the particle moves through quadrant 2, retracing phase 2. So in fact, phases 3 and 4 are just retracing the steps for phases 1 and 2, but we had to check that. And of course, by periodicity, we're just repeating the behavior overall. All right, don't forget your arrow. Okay, you have to put at least one indicating orientation. It will be counterclockwise in our class. Okay, and on a final, I would allow either using Cartesian or graph paper. I'll provide both, basically. All right, so next up, I'm going to talk about how you can figure out it's a circle analytically using algebra and quickly look at another example.